Okay, great. Can everybody see my screen? Again, this says quiz 3 practice.
Yes.
All right, thank you. Thanks a lot. Okay, let's take a look at the first one. For the following reaction, which functions as an acid? So this is just a matter of labeling an acid and a base, and then a conjugate acid and a conjugate base if you want to. But you can see that this molecule, the ketone here, is donating a proton to this oxygen with a negative charge. And so that must be this would be our acid. This would be our base over here. And so the answer is 2. And if you want to label the conjugate acid and the conjugate base, this is our conjugate base, and this is our conjugate acid. So just some practice on labeling acids and bases. Next question says, draw the conjugate acid of this molecule. Could anybody tell me which functional group is in this molecule? A little functional group practice.
Ether?
Yeah, absolutely. This is an ether. So this is an ether, okay? This is called dimethyl ether. Again, you don't need to know that for the quiz, but there you go. So dimethyl ether. Anyhow, if we draw the structure partially condensed for dimethyl ether, you know that there's 2 lone pairs on the oxygen. So if dimethyl ether behaves as a base and it accepts a proton, then we're going to end up with a conjugate acid. So it's going to accept H plus, and it's going to accept it on the oxygen like this. And so this would be the conjugate acid of dimethyl ether. Okay, if you don't like the way that I have it written out like this, another way that you could write it is you could just say, what's going to happen when I put dimethyl ether? So let's write it out again, dimethyl ether. If I put dimethyl ether in, a strong acid like hydronium, right, I'm going to get an equilibrium. We're going to have the conjugate acid that I just drew. I'll just draw it a little bit differently this time, and you're going to be left over with water. So again, this is our acid. The dimethyl ether is behaving as a base. This is our conjugate acid, which is what we wanted, and then water is our conjugate base. Okay. Next thing here, could anybody tell me the functional group in this compound? Do some more functional group practice.
Ketone.
Absolutely, yeah. This is a ketone. This is called butanone. So we could draw the lone pairs in like this, okay? And what would happen if we put that in a strong acid like hydronium? What we could do here is we could draw the full Lewis structure, and we could practice our curved arrows, right? Because we know that if we want to draw the conjugate acid of the ketone, it's going to be behaving as a base. It's going to donate a pair of electrons like this. Then we're going to draw the 2 curved arrows. So we're going to end up with the oxygen on the carbonyl being protonated like this. We call that an oxonium. Fix up my positive charge here. An oxonium like that. And we'll be left over with water. So again, we could label just some practice. Here's our acid. The ketone is behaving as a base. This is our conjugate acid. And this is our conjugate base. Like that. There we go. Next one says draw the conjugate base of this molecule. So this is called propyne. Anyhow, if we want to draw the conjugate base, it's going to lose a proton, right? It's going to lose a proton. So if we were to put this in a really strong base, I'll just use a generic B for now. But if we were to take this, this compound, and remember that the protons on the CH3, those have a really high pKa, right? They have a pKa of around 50. This one is on the sp hybridized carbon directly attached to it. It's got a pKa of around 25, right? So if I put that, if I put that in a really strong base, so I'll just use B minus here. You could use anything. I mean, let's just keep it simple for now. Anyhow, if we draw what's going to happen there, the base is going to attack, right? Take the proton like this, and the conjugate base is going to look something like this. We have our CH3, our carbon with a triple bond, and a lone pair and a negative charge, right? And then we're going to be left over with our BH, like that. So this is our acid, this is our base, this is our conjugate base, and this is our conjugate acid, like that. Next question, more of the same, just labeling conjugate acids and conjugate bases. You know, you see sodium hydroxide, it's probably a good clue that that's going to be your base, right? Sodium hydroxide is a very strong base. And also you can see that the hydroxide is taking on a proton to form water. Now, something that's interesting in this one is that the spectator ion is shown, isn't it? Right? We left the counter ion in there. So, I mean, the counter ion's not playing a role, but it's left in. There's nothing wrong with that. But you can see how sodium hydroxide is behaving as a base, right? Could anybody tell me this functional group, the SH?
Thiol.
Yep, perfect. Right, this is a thiol. So this is ethane thiol, a really smelly compound. Anyhow, so you have your acid, oops, your acid, your base. You have your conjugate acid, and your conjugate base. And so the conjugate acid is water, which is number 4. All right, let's move on from there. Okay, another reaction where you see the spectator ion. You see the counter ion, the lithium on the far right there. Anyhow, it says, what's the conjugate acid in this reaction? Well, you know, more practice, we can see that this molecule is taking a proton, right? It's accepting a proton because you're left over with ethane in the end. So this must be our base, right? We're donating a proton, one of these protons. So this is our acid, right? This is our conjugate base, and this is our conjugate acid, like that. And so we want to label the conjugate acid, and so that's number 4. Oops.
I have a question
Go
about
for it.
this. Did you say that the acid was donating a proton?
Yes.
Okay, because I thought that acids accepted protons. Is that correct?
No, that's totally incorrect. So with the Bronsted-Lowry definition, so Bronsted-Lowry, right, definition is an acid donates H plus and a base accepts H plus. Think about any acid that you can remember from general chemistry, right? What are some acids you would know? Sulfuric acid, nitric acid, perchloric acid maybe, hydroiodic acid, hydrobromic acid, hydrochloric acid. Those are some strong acids. What do they all do when you put them in water, right? We talked about the leveling effect. They all donate H plus, right? That's the function of an acid. You think about bases, what are some bases that you know? Well, the most common base you know from general chemistry is hydroxide. What does that do? It accepts a proton. Does that help?
Yes, thank you.
Okay, good. All right, well, let's move on. Again, label the acid, base, conjugate base. Here they've left out the proton, of course, because this is a bond line structure, but this is the acidic proton here. You can see that this must be behaving as an acid because it's lost a proton. So here's our acid, here's our base, this is our conjugate acid, and this is our conjugate base. There we go. That was pretty quick. Here it's asking us to provide a curved arrow mechanism for the following acid-base reaction. Look, sometimes if you print things out, like if you were to print this out, you know, in your printer at home, or if you're using a tablet, like what I would recommend here is you don't have a lot of room to draw the curved arrow. So I like to redraw ions or molecules if I don't have enough space. So I'll just redraw the hydroxide like this. We can even scratch that out. And that's just so that I can draw my curved arrows, more effectively. Anyhow, let's put in the lone pairs that are missing. There's 2 on the sulfur here. There's 3 on this sulfide, or sorry, this, yeah, 3 on the sulfur with the negative charge, and we get the water. Anyhow, you can see that the hydroxide is behaving as a base, right? The thiol is behaving as an acid. It's donating a proton. And so to draw our curved arrows, we're going to start on a pair of electrons from the base. It's going to attack the hydrogen. Okay, a base is a proton acceptor. And then the acid is the proton donor, right? And based on the Lewis acid definition, the Lewis is the electron acceptor. It makes total sense, right? We have an electron acceptor, our Lewis acid, and the Lewis base is donating protons. There we go. So there's a curved arrow mechanism. All right, we could even draw one for this reaction here. It doesn't ask us to do it, but again, we could do more of the same. We could redraw the hydroxide because that's our base. It's the proton acceptor. We're going to draw a curved arrow from a pair of electrons on the hydroxide. It's going to attack the proton, right? A base is a proton acceptor or an electron donor, and the acid is going to donate the proton, and it's going to accept those electrons, right, to form this anion right here. So that's something you can always do with acid-base chemistries. You can always practice your curved arrows. Another one here, we got to practice our curved arrows. I think a good first step is usually to draw in your lone pairs. So we're missing a pair here, we're missing a pair here. All right, well, who's behaving as an acid and a base? I see a lot of nitrogens here, you know, but you can clearly see that this molecule here is donating a hydrogen, right? It's only got 2 over here and it's got 3 there on the nitrogen. So this must be our acid, and this must be our base. The base is the proton acceptor. So I'm going to draw an arrow, curved arrow from the lone pair, and I'm going to take one of the hydrogens. Like, just some semantics here. The students get bogged down in sometimes. It doesn't matter where the curved arrow goes. It can go anywhere, okay, as long as it gets to the proton. Now that is ridiculous. I would grade that incorrect. It looks so crazy. That you can draw it from the top, doesn't matter. You just need to abstract one of those hydrogens. It can be the hydrogen over here. Choose whichever one you like the most, okay? It's going to attack the hydrogen, take it. The acid is going to be the electron acceptor, the proton donor, right? And there you go. There we have our curved arrows. Give me a thumbs up if you follow me on the curved arrows, or if you have a question about these curved arrows, feel free to ask me. You can stop me anytime and ask me a question. All right. Are we feeling a little more confident? Now that you know, some practice will always make you feel more confident. One thing I find about organic chemistry, I mean, I studied it for a long time. Even when I was in graduate school, sometimes I'd learn something, some new theory that I wasn't really familiar with, and I'd hear it in class and be like, what is this? I'll never figure this out. Then I'd go to the office, you know, where I was studying, and I'd sit down for an hour and be like, oh, okay, I guess it's not that bad. You know, once you take some time to really look at it. Here it's asking us to identify an acid and a base, provide a curved arrow mechanism. I'm going to redraw the base. Just, I find it's easier since you can't really see the lone pair. So we'll draw those in like that. Okay, so there we go. This is our base, right? It's accepting a proton. That's why we end up with ammonia over here. So therefore, this is our acid. Now, which proton is being donated? This is kind of interesting because you see the negative charge is on this carbon here. So that means you're going to have to draw a hydrogen in, right? There are 2 hydrogens here, absolutely. But something you'll see organic chemists do all the time is they'll only draw one of them, just the one that's, you know, just to show the mechanism. I'll leave both of them in since we're just learning the subject. And I'm going to draw my base, start on a pair of electrons. It's going to attack the proton. Remember, a base is a proton acceptor. An acid is a proton donor. It's also an electron acceptor. So I'm going to draw a curved arrow like that. I could even put my lone pair over here next to my negative charge since you can't see them. There you go, like that. Okay, here's a reaction where we see the curved arrows drawn for us, but there's 3 curved arrows, aren't there? Right, there's 3 curved arrows here. So the first curved arrow, and I'm going to start over here on the hydroxide, it's our base, is going to pull off that proton, right? And then you're breaking that sigma bond right there. So one of the products is going to be H2O, right? When you take hydroxide and you add a proton to it, you get H2O. So there we go. So there's that. But then what's going to result from these two curved arrows here, right? And I'm talking about this one and this one. Well, let's draw. If you're really confused, you're like, I'm not sure what it is, start by drawing the parts that haven't changed. Okay, so draw everything. This bond didn't get touched. This bond didn't get touched. This bond is still there. But let's analyze this really carefully. Look, I have a curved arrow starting on this bond. That's a pair of electrons, and then I'm ending the curved arrow between this carbon and oxygen. That means there's going to be a double bond between this carbon and this oxygen. Now, where are these electrons going? Let's look carefully. The arrow, the tail starts on the middle of that pi bond. It's a pair of electrons, and the head ends up on this carbon right here. So that tells me that there's going to be a pair of electrons on that carbon. Now, where is, sorry, I just went ahead and drew the negative charge in. Anyhow, so there's my negative charge. And since you have the positive charge over here, you have to draw it on this side. Now I'm going to draw it next to the negative charge. Why? Because the cation is going to be attracted to the anion. So it's proper to draw them near each other. All right. There we go. So that's predicting the products. The next one is just some general chemistry too, right? You all studied general chemistry too. You can't throw that out the window and say, oh, I just passed it, forget it. No, it doesn't work that way. If we want to draw our K equilibrium, you should remember, and this is just a review, that if we have a reaction like A plus B is in equilibrium with C plus D, then K equilibrium is equal to C to the power of C times D to the power of D over A to the power of A and B to the power of B, right? This is general chemistry 2, okay? So we have our K equilibrium here. But what do we leave out in this expression? Is there anything that we would leave out in our equilibrium expression? The answer is yes. We leave out water because its concentration remains constant. And so we're going to have the concentration of our product in the numerator. Sorry, I'm getting ahead of myself here. I'm thinking of Ka. My bad, I made a mistake. Okay, so and this is in my slides too. Okay, so in the K equilibrium, yes, we do include water. So in the Ka, you leave water out. My mistake. So anyhow, we have the concentration of the conjugate acid times the conjugate base divided by the concentration of the acid times the base. So the answer would be 3. Okay, so again, if you're like, what did you get confused, Mr. Dion? I got this confused. Okay, I got too much equilibrium on the brain here. When you do write out the Ka, you would leave water out. Okay, you would just write this expression, but you'd leave the water out of there. Okay, that's all. All right, there we go. Let's move on. Which one of these compounds is the most acidic? Well, you got a couple of options here. You could try to solve this qualitatively. You could try to use pKa's, right? That's one thing you could do. I like to use pKa's. You spend so much time memorizing them. The pK of this molecule is 19, a ketone. The pK of a carboxylic acid, this one's 4.75. Let's just call it 5. The pK of an amine, one of my students told me today, it was 38. And this, we're not even going to find the pK of this. This is the conjugate base of 2. So conjugate base of 2. And you're wondering, is there a pK associated with this ion? Absolutely there is, but we're not concerned about it because it's so far off the scale. So the
Mr.
answer,
Dion,
yeah, go ahead.
I thought for the first one that would be negative negative 7.3 for
No,
the ketone.
no, not a ketone. A ketone is going to have a pK of around 19. So this one has a pK of around 19. When you have a pK of minus 7.3, that's when you have a protonated carbonyl, like this. This proton has a pKa of minus 1.7. Okay? When we're talking about the pK of this ketone, we're talking about this hydrogen here, right? That would be the acidic hydrogen there. Does that help?
Yes, thank you.
Oh, no problem. All right. Let's see here. So which one of these is the most acidic? So whichever one has the lowest pKa, there you go. So somebody asked a question on the chat. They said in table 3.1, it looks like we should associate pKa values with functional groups. Example, all alkanes have a pKa of 50, independent of the number of carbons. Absolutely, 100% correct. So if you have a hydrocarbon with 1 carbon, 2 carbons, so if you have, if you have propane, or if you have butane, or if you have pentane, they're all going to have a pKa of 50. If you have an amine, all amines are going to have a pKa of around 38. If you have a ketone, they're all going to have a pKa of around 19, so on and so forth. So yes, you associate them with functional groups. Think about the alcohols that we saw, okay? Except for phenol, which is a special class of alcohol, they all had pKa's in the neighborhood of 16 to 18. All right, so that's the kind of rationale that you want to take when you're looking at pKa's.